Recording and transcription. Hello. Oh, you are right. Good catch. Share. Here's the thing. Yeah, I think screen is just in case. We're gonna switch screens like once or twice. Yeah. I reckon it's good to get started. Okay. Can you see that? You can see that. Okay, let's not share window. Let's see. I share this and it's like that. Oh, right. Yeah. All right. We're gonna get started. So, surprisingly, today we're going to go over Julia for scientific computing. We're going to skip over a lot of things that are more CS about the language. We'll do a very brief introduction to strings and everything like that. But we'll start by actually describing the language. Let's turn the Club Penguin music off for a second. Perfect. Okay. So Julia is a dynamically typed and compiled language designed for numerical analysis primarily. Dynamically typed essentially means that you don't have to define the types of variables or functions before you actually run them on your compiler. And dynamically compiled also means that the functions are checked at runtime. So it was launched in 2012, and it's distinguished by something we call multiple dispatch. We'll go over it later. It being almost as fast as C. You can call other libraries very easily, and something they call just ahead of time compiling, which is a little bit of a misnomer. Essentially, it means we run things at runtime, but the types are actually checked prior to runtime. And we'll see some of the consequences of that in some later slides, or on the notebook, I think. So here are some benchmarks. It's a little hard to look at this plot. Julie is about over here. You can see my mouse. And when it gets to 10 to the 0, it performs as well as C for each particular algorithm. To see it a bit better, we'll look at this benchmark chart. For pretty much every algorithm, it's approaching the efficiency of C algorithms themselves, which is a very good thing. C is probably the best language for any type of numerical analysis, maybe closely followed by Fortran. But there are still a lot of flaws that we might or might not go through. One of them is the startup time is within an order of magnitude of 1 second, usually more. Another thing is that the compiler has this algorithm that it runs every time it actually runs your code. And so there's an overhead cost in time for each function definition. And the code, when you run it like Python, it's significantly slower than running it like C. We'll show you what that kind of means in some of the future slides. I wanted to go over installation, but what we're going to use today is this specific link. So if you have access to the PowerPoint, you can just click it. If not, you can just type this link into your search bar and it'll work. We're going to do all this on cloud. We're going to precompile every package so that it runs really quickly, and you guys don't have to install anything. So I'll give you guys a couple of minutes, and you can just click this, or you can type it into your search bar really quick. Is everyone good with it? Okay, we'll just get to the notebook then. I'll click it too, so it's like I'm here or something. Let's close this. It takes a while to load. So here's a Jupyter notebook. We're going to have two different notebooks here. One of them is the empty one. It might take a bit to load too. And then one of these is actually the full one. It has pretty much everything we're going to go over. And if you find yourself a little late through the workshop, you can consult this and get to where we're at and run things yourself. It's got the whole thing. It's a lot of stuff. But we're going to start with the empty one. Let me adjust. Is this doing it? Yeah, I think this is good. Can you guys see this fine? Okay. All right. We're going to start with variables and data types. So it's very analogous to Python or MATLAB if you've dealt with any of those languages. Julia is dynamically typed, meaning that the types are checked at runtime, and the types don't need to be explicitly specified. So the variables are case sensitive, and any UTF-8 character is allowed. The only things that aren't allowed are keywords that we'll go over later. So by UTF-8, I mean something like, see, if you put a slash and something like a variable you can think of, a Greek letter, and then you press tab, you can type a delta. So that's something that can also work as a variable. This is just kind of a feature of Jupyter Notebook. We'll start assigning our first variable. We have here x is equal to 1. Cool. If we just prompt x here, it's going to return the result of the cell, which is 1. And furthermore, we can just provide an operation here, and it's going to give us what x plus 1 is equal to. Let's see. Actually, I'll do this. Is this still good to see? Okay, cool. Any questions in the middle of the lecture or the workshop are totally fine. So if I'm going a bit fast, tell me, especially you, Brandon. You kind of have to monitor me, okay? Okay. Okay, sorry. You're my caretaker right now. So we have this function here, println. This just prints a line. There's also a regular print function in Julia, but we'll kind of see what happens if you put two print functions. We'll say print x and print x. It's going to put them together. So x here is still equal to 1. If we put println on these, it's going to print them separately. Furthermore, we'll see that we can reassign x again. The operation that we performed here doesn't reassign x's value. It only prompts it up when we run it. So here we're reassigning x, and we'll print it again. And obviously it's equal to 2. Furthermore, you can provide the same operation here, which is x is equal to x plus 1 in a different way. We can say x plus equal to 1. So this just adds 1 to an existing x and reassigns it. And now x is equal to 3. Yes.
So it looks like sometimes you're using semicolons. Why is that?
Good question. They're totally optional. We're actually going to go over here, but it's better if we go over it sooner, I think. A semicolon suppresses the output. So if I run the same code here with a semicolon, it just doesn't print anything. And it only prints something without the semicolon if that's the last element. So for example, here, this still doesn't print anything because this is the last line in the code. So thank you for your question. That's a good question. And if I ask questions and nobody answers, Brandon, you have to, is that good? Well, let's say you said yes. Anyways, with a typeof function, we can check the type of a specific variable. So we'll define a new one here. Let's say L is equal to 1 dot. So the 1 dot here, previously we were just putting integers as our variables, but when you put the dot, it turns it into a float, which is pretty much just a real number, I think is the best description of it. It has decimals after it. So if we wanted to put this, it goes 1.0 instead of simply 1. Everything good over there? Oh, okay. Do you want to just type in this link over here, like into your search bar? You can just type it. It's also in the Discord. Sure. Or Brandon, can you actually do that? Yeah. Oh, cool. Great. Where's this thing? How do I get this out, Brandon? Okay. Thank you. I'm not a corporate guy. I don't use Teams. Um, feel free if you feel a little bit behind. There's a notebook with pretty much everything on it. We were here. So we define a float here. It's essentially 1. And we'll say print this float. Or let's go ahead and say print the type of this float. So here it's going to say, oh, it's a float with 64 bits. And then we can print the same thing. We can print our x. And we say it's an integer with 64 bits. So note that Julia lets you redefine built-in constants or functions. And this is really, really bad because if Julia has, for example, pi or like a function like a square root saved and you redefine that, then you got to restart your kernel and do it all over again, which is always going to be a little bit silly. So pi, for example, is going to be pi, but we can say pi is equal to, say it's equal to 1314. Yeah, better with this keyword. 1314. I'll say engineer mode. Okay, fine.
Pi equal b.
Yeah, I'll define this actual pi here. Mhm.
Sorry. Like, you don't need a semicolon? I think you.
Yeah, you never need a semicolon, but if you don't put a semicolon, and if that is your last line for your cell, this is your cell, then it's going to print it out. So, sound valuable. This is silly. Does this work? Okay, I'm going to restart the kernel. I'm going to run all of this again. And then I'm going to assign fine is equal to 3. You don't need to do this yourself. This is kind of just a little demo, a really bad one too. Perfect. Next. God. So we've reassigned pi to 3. That's very silly. Obviously, we want more decimal places. So that's something you have to watch out for when you use Julia, which is why I talked to Kyle about it being bad from shell. You were going to forget that you redefined something really important. So we're going to say square root of 4. If we have called our square root function, it's kind of already in our system. So if we try to redefine the square root now, let's say square root is equal to 4, then it's going to say, oh, we can assign this. It's already on the main module. So we can define variables with existing operators too. So this is going to be a function, and we'll go over those later. This is f is equal to plus. So now our f just performs an addition. You'll see that the addition here has 206 methods. That means that for 206 different data types, it performs a different operation. This is part of multiple dispatch, and we'll go over that later. But now that we have our f, it's just going to do addition of any elements you choose. So this is a type float here. It's a 1. And this is an integer. This is a 2. And it'll do an addition. 1 plus 2 is equal to 3. Crazy. We'll just kind of look at this. These are all the types. You can look at that if you'd like, but we're not going to look at it. So for each of these types, we can actually define the type min and type max of those types. So I'll pop this up again. The smallest value is your type min, and your largest value is your type max. And if you ever subtract one number from the smallest value, it'll loop back around. So it'll go to your highest value. And if you ever do the same with the largest value, you add a 1, it'll go back to your smallest value. So it kind of goes in a circle. So for example, if we say type min of int 8, This is negative 128, which is 2 to the 7, or negative 2 to the 7. If we subtract 1 from this, or okay, this did not work. Let's do int 8 type min. By default, everything is in 64 bits. An exact error chunk. Okay, we'll do this how it's actually in my notes. Sorry about that. We'll print ln, or we'll just do an int64. So we'll do type max of int64, which is our default type for integers in Julia, and we'll do +1. And you'll notice it actually goes to a negative value. If we take away this +1, it goes to the other side. So you ought to set your type for what type of operation you're doing. Typically the smaller types, so int 8 and float 16, are going to be quicker to run. They're going to hold less in memory, but it's usually pretty negligible. So we'll do z is equal to 1. It kind of shows something. This here is an int type, but it's very easy to make it a float. There is very simple commutativity between these types because they're very, very similar. They kind of have the same primitive type, or like, you know, these are like, they have the same grandpa, I guess. So that, you know, they're kind of related. We'll say, just to show this again, z is equal to 127, int 8. We can put this into int 8, 0.127. We can add 1 to it. It'll say an exact error. Furthermore, we can define everything in terms of bits. So one thing that's very curious is there's a different variable saved for 0 and for -0. So if we say bit string 0, it's going to give you the bit representation of a 0. We can copy and paste this again, though. Let's define this as something different, and we'll make it negative. We'll do this in a separate cell over here. You can add a cell just by clicking the insert cell button here. We'll run this again. And we'll see that -0 is actually stored as a different bit. If there's any use for this, I would love to know. But for now, we'll just mention it. We'll put it out there. There's also a representation of, you know, infinites. For sure.
What part? What is the difference between, what does that mean, like the position and stuff like that? Precision, with precision.
Oh, precision. So it's more of a, just from my understanding, it's like a way we call these numbers. So we call double floats a float that has a specific difference between its minimum value and its next value. These are just names for it, from what I know.
So if you float 16 instead, you just look at the same answer.
Yes, it depends. So if we do the type max of this, or if we do the type max of float 64, well, it's going to be infinite. But they're different infinites. The sort of point is that your float 32 goes to less significant figures. So for example, I think float 32 single precision goes to -16 or +16. 1 times 10 to the -16, 1 times 10 to the +16. But float 64, I believe, does 10 to the 22nd and 10 to the -22nd. And so it also means that between, like, let's say you want to see, oh, what's this next smallest number that I can actually represent in my computer? A float 64 also has a smaller difference, so more accuracy, which is why it goes to 1 times 10 to the -22. The difference between two numbers can be that much. Yes, essentially. I mean, that's really it. Space is the good answer. It's likely slightly faster, but that difference has always, like, I've never seen it not be negligible. But if you're, for example, doing a big array, float 64, I don't know. Yeah, that's what I think. Exactly, because if you have like a 2 GB array in, or like a 4 GB array in float 16 and you go to float 64, that's going to be more than your RAM because 4 times 4 is equal to 16. Crazy. But yeah, that's going to go over your RAM and you can't store that array ever. So thanks for the twin, Kyle. I didn't know.
That's an absolute unit of an array right there, though. I mean, that's absolutely gigantic.
You'd be surprised. For all the projects I've done, it's super common to see arrays that big. So one thing we do is we save every like nth point in an array. So if I wanted to plot something and I needed 100 million digits to guarantee that like a discontinuity is well represented by my array, then I would. Oh, another question. Sorry. I would save that not in memory, but I would save every 100th point in memory, and that's 100th the size of the array, but this continuity is still well represented. Does that make sense? Yeah, I think we've already. You can type here, and there's not always good representations of everything. For example, I think if you do, and I guess we can try it. If we do like z is equal to 1.2, and then we do int 8 of z, I think it might just round it, or it'll say, yeah, inexact error. I think if we do 1.0, it just goes to 1. In Python, it would actually just round it to 1 or 2. I don't know. Yeah, I think it truncates. But yeah, that's something to keep in mind. Julia has a few different quirks from Python, most of them good, but some of them, for example, I would prefer if it popped up an error, just in case. Anyways, we'll go back to where we're at. We can represent numbers that don't converge, things like infinity. And we can also use infinities in our calculations. So infinity not defined. Oh my goodness. Yes, thank you. So 1 over infinity is going to give you 0. You can also play around with this quite a bit. I think it's pretty fun. Infinity plus infinity is obviously infinity, but if you do infinity minus infinity, it's not a number because you can't really. There are bigger infinities than others. This is like some higher level math terms. Pretty unimportant in general. But it's very interesting to look at some of these cases. So we can do print ln, not a number, is equal to not a number. Turns out that's false. And we can do the same thing and say not a number is not equal to not a number. We'll go over some of these operations later, but this is what that means. And it's going to say this is false and this is true. And it doesn't really matter what not a number you pick, that's always going to be true. Furthermore, what we were talking about before, the EPS function is going to tell you the minimum distance between 2 points for your specific data type. So, for example, if we do EPS, it's going to default to this is the same as EPS float 64. So this is the minimum distance between 1 point in float 64 and the next point. And we can do the same thing with, we'll copy and paste this. Float 64 or float 32. And it's going to tell us the minimum difference in float 32, which is kind of a big deal. You know, if you go to nanometers, you know, that's a very useful unit to people. It's not even representable by float 32. So you're going to loop back around multiple times. Furthermore, we can take the actually, no, this is not good to go over. We'll go over something silly. Big int. What's up?
Why is it f minus 7 instead of e minus 7?
That's a good question. I have no idea. It's the same thing. Yeah, you can represent them as both. I think it's just a matter of like whoever coded this was like, I'll write this as f negative 7. It's 2 different end terms. Yeah, that's a good point. I can't think of a reason why you would ever do that. So big int is something really silly. I think Kyle asked about this one time. So there's no way. Yeah. So if we do this in big int, the type max of int64 is going to be its maximum. If we added 1 to that, it would loop over since we've gone to the maximum. But if we do big int type max plus 1, it just adds 1 to the actual type max. So we can see it here again. We can see what adding 1 does. It doesn't loop back around. So we've made some use of a kind of silly, cringy data type. Furthermore, there's big float. I didn't name these. So we'll do 1.0 over 9. And big float represents a lot of digits, but it kind of trails off here, and you can see where it kind of goes wrong. Yeah, I couldn't tell you why this happens. It probably has to do with the epsilon, but it's nothing you have to really keep track of. There are a couple of extra cells here that I'm just going to delete. Next, we'll go over strings. So we'll say stupid is equal to hi guys. So now we've made a string. Pretty simple. We can print the string and it won't add the quotations. So we'll print stupid. Hi guys, no quotations. Perfect. Furthermore, you can actually do the exact same thing, but we'll pick stupid here. And we'll add 2 quotation marks around each of these. And this is also a string. The only difference is that if I said something like, hi, guys, quotations, it doesn't look great, but when we print it, it's going to actually have the quotations. It'd be a little troublesome if your system thought you included a string here. So that's why the triple quotations are here to kind of specify. Let's see. And we can also take something like stupid over here, and we can add a bunch of spaces. Serious. Let's print this, actually. Stupid. Hi, guys. Serious. And so we've added this space here. This is kind of different from Python. You have to go through a lot of trouble just to add different rows. You have to type /n every time. I don't believe so. I think you can just do, we'll copy and paste this. And then not juxtapose. Yeah, I guess it doesn't seem like you can do, or this is the problem. Yeah, it could still do the enters. You would probably, and that's a very specific case. I mean, this is the same as tapping /n. So I can't think of a case where like this would deter you at all. I don't know. Can you think of like a French example? Oh, I see. I think you can also do /n, just in case you wanted to do that. So yeah, this goes on a different line. /n goes one more line, just in case you wanted to do that. So you can actually just use your regular syntax. I'm pretty sure. I'm guessing C also does this. I know Python does /n is a different thing. And then we'll do y is equal to 10. And we'll have this new concept. It's called string interpolation, just in case you wanted to know what the term is. So the amount of toes I have is $. So inside the $, every single variable is going to come out as a string. So we can type y, but let's also do y plus 4 to kind of show the functionality here. The amount of toes I gave, the amount of toes I have is 14. And you can change this to any sort of variable. It's a very easy way to include your numbers into strings. By the colon operator. So yeah, this is what we have here. I added a few cells. This is a little silly. And then we have the sort of multiplication operator. It's defined for strings. So we'll say 1 is equal to God is, 2 is equal to me. 3 is equal to say 1 years old. So we can print ln, and this multiplication, when it takes in two strings, it's just going to stitch them together. So God is me. And then we can do 1 times 3. God is 1 years old. We'll skip a little bit of, or no, actually, I think we can go over complex numbers. Z is equal to 1 plus 2m. This is just a complex number. Every single method we've looked at, including sums and multiplication, is defined specifically for this. So this is our Z. And it has a real value, so we can say z.real. Complex system field. Are you kidding me? Oh, that's a method. So real Z, and I'll tell you the real value, and then we can do imag, so the imaginary component of Z, which is 2. We'll skip over to data structures. The most common one that everyone probably has heard of is an array. So here is an array. If you're in math, you probably want to think of this as a vector or a matrix. If you're in CS, you just think of this as something that holds values, whether that's a number or a string. For arrays, we can index them, which means we can call a value from the array. I have a question for all of y'all. Who prefers when your index starts at 1 over 0? Is there anybody here?
0, not one soul. Honestly, I've never met someone.
No. Really? Okay. So personally, I think of it as a real number line. Like on a real number line, you would start at 0 if you wanted to represent the same thing, and then you go to 1, 2, 3, 4. So that's how I think about it. If you try to call list 1, it gets the first element over here. If you try to call list 0, it'll be like we're not in Python. That's a little silly.
Should actually be an error method.
I wish. It'd be very accurate. And we can define this list not only as a new array, but we can define its first element as list 6. And we can print the list here, and it'll say, wow, we've changed the first element to 6. Furthermore, we can actually make this have multiple data types. You can see how this would be easy with like integers and floats. But if you have something like a string and a 1 here, it still makes the 2-element vector. But now the vector says this is an any array, which has some consequences. Particularly, the type inference algorithm is going to run slower on that. Or this is it. I'm skipping ahead. We have tuples here. Tuples are like arrays, but they're immutable. So you can never change them from the inside like we did here. So we just do what is this, a circle bracket instead of a square bracket, and this is your tuple. Cool. If we try to refer to an element in a tuple, or oops, wait, am I stupid? Or no, if we try to define a new element in a tuple, it's going to say this is not something you can do. A tuple, I feel obligated to say this, but I've never used this in my entire life. You can assign different named values. So we can say the variable 4 is equal to string 4. The variable 5 is equal to string 5. Yeah, I mean, typically you would do this with like a dictionary. You can say tup.4. It's going to tell you what the 4 value corresponds to over here. You can do the same thing with dictionaries, or let's just show that we can still index here, and it's going to give us the value here instead of whatever you define it as. Dictionaries are like this a named tuple. you kind of just relate two elements to each other, and the variables, when they're printed out console, are going to be ordered alphabetically. A dictionary is just defined as dict, and then we can say name, and then you put equals, like a little arrow. You can say age is equal to arrow here, 22. Find. Oops. Yeah, they have to be strings. You'll notice that we typed the name first and it's showing up last. So that's because there's no use in like indexing dictionaries to begin with. So there's no point in them being ordered by how you define them. There's more use in them being ordered alphabetically, because then you can kind of sort of ascertain where everything is going to be. So we can refer back to dictionaries, not with an index, but with whatever you defined an element with. So here we're indexing by the term age, and it's going to give us back what age is defined as. We'll go to operations, a little more interesting. So here we'll define a variable n. N is equal to 2. We have this operator. This is the identity operator. It just returns back whatever you put in. We have the inverse of that, which defines the negative. We have addition, super cool. We have subtraction, also very cool. And you can kind of see where I'm going with this. We have multiplication, we have division. We have something which is more interesting. I think this is, is this div? Yeah, this is /div tab is going to give you this division. What this does is it's an integer division. So you'll notice the output here, even though we have an integer as our input, the output is a float. Over here, it's an integer output. We can do, this is the power of 2. In most languages, or I guess in Python, you would actually do 2 multiplications. This is way more intuitive, I think. And then we have, this is sort of like division, but kind of the inverse. So if you do n, is this backslash or forward slash? Does anybody know? Yeah, if you do backslash instead, it'll do 1 over n, which is 1 over 2, 0.5. We can get the remainder. It's surprisingly useful. The remainder of division by 3, you're dividing 2 by 3, so it's not even going to fit 1 times into it. So it's going to be a remainder of 2. And then, as shown before, we can do all of these operations and put them before an equals to redefine our variable. So this is going to redefine n to what n was before minus 2, so 0. So multiplication is implied in Julia, and what that means is if you do something like 2v, clearly what you mean to do is multiply v by 2, but in Python this pops up an error because you didn't add a multiplication here. And this clearly works. In general, makes writing things way less error prone. It's the same thing as just putting the multiplication here. Here are a bunch of operators. A lot of them are very intuitive. We have all of the logical ones. So the logical ones are like negation. This is and, this is or. And then we have the equality, inequality, and then all of the comparisons. So we can say s is equal to true. It's going to return true. And then if we do negation of x, so the negative of s, it's going to equal to false. If we do s and negative s, this is going to be true and false, which is false. But if we take this here and we replace it with or instead, all we need for an or to be true is for one of the elements to be true. Yes.
Do we have like the non-short circuiting and an or?
Yes, we
just not bother to use them because of.
It's more of a, I had enough things to include here, and that's probably one of the least important ones I've thought of. It's great that you're asking about that. So there's a doc here. You can check those operators there too. I'm pretty sure it's on the same page if you look around. But yes, there are like the short circuiting ones.
Yeah, make your really make a distinction. There's probably like one situation.
Yeah, there's one situation where a CS major would use it. You know, we're here to just do numerics, which is the good thing about teaching it this way. Here we have the comparisons, and I'm not going to go over this too in depth, but you know, 2 is not bigger than 3, so that's false. But 2 is smaller than 3, so that's true. Next, we'll go over broadcasting. So broadcasting, the point of this discussion is an array in Julia can be a vector, or it can be represented as just a list of elements. So with a vector, you have like matrix operations, or with a matrix, you have matrix operations. But with a list, you pretty much want to do everything element-wise, which is to say, like each element goes through the same operation. So we'll define a list here. This is going to be analogous to a matrix. So 3, 4. And then we'll do dot multiplication to represent an array operation. So this is going to multiply every element by 2. Now, it just so happens that this is the same as doing it without the dot, but there are cases where this is pretty important. So for example, list to the power of 2 is just going to score every element in the list, but without the dot, it's going to do the matrix squared, which is very different. We'll turn this back to multiplication. This is the same thing as using the map function and then saying x maps to x times 2. And we do this for every element in list. If we just do a simple multiplication, like let's say list times list, it's going to do the matrix squared. If we do list times list, element-wise, it's going to give you a very different result. So here's a cringy little example. So for a matrix X, you can define the cosine as this. You don't need to look at it too hard. We'll just do it. And this is what happens when you apply the cosine function in Julia, which can take in matrices. It's going to do this very heavy operation. I don't know about this one. Yeah, cool. This is very different than doing it element-wise for list. And you can do this with pretty much any function. Here we're doing it with cosine. This means just apply cosine to every single individual element. And that's going to be different than doing the cosine of the matrix.
The exponentiations are all like matrix multiplication instead of like lines.
Yes. Yeah. Have you seen exponential of a matrix? That's something that actually is taught in math a lot. It's like it's an abstract way of representing like a particular type of data. So you can do this with like tensors too. I guess there should be an abstract way of doing this, and it's going to look very different. And this is the only way to do cosine with a matrix. Typically, you're never going to do that, so you don't need to think about it too much. We'll do list, and then we'll do the list times the inverse of the list. So this is matrix multiplication. A list or an array times its inverse is going to give you an identity matrix. But hey, it actually has a little bit of numerical error here, so I'm going to try to round it. The round function rounds things. So we'll do list times inverse of list. But oh no, it doesn't work. Does anybody want to tell me why? Yes.
The dot.
Perfect. Wow, now it does it for every element, and it rounds it. Thank you, Brandon. All right, we'll go to functions. So a function is pretty simple. We can define a function by typing function, your representative variable, and then this is the input. So function g of x is going to be x times 10. And every function is terminated with end. This can be really useful when you have long blocks of code and you don't know where it starts and it ends, as you'd think. And if we put g out there, it's going to say it's a generic function with exactly one method. We're going to see Ethan. Yeah. We're going to do g of 10, so g input, and as you'd guess, 10 times 10 is 100. Now, the thing that we did here is we never said what it returns, so by default, it's going to say that g of x is your last line of code. There are a myriad of cases where you don't want that to be the case. You don't want to return the last thing defined. So you might want to print something after you define it. That's the best example I can think of. But return here does sort of the same thing. We define the same g of x. And it's going to function like let's say this is r of x. Or complete function. Oop. There we go. This is the same thing as g of 10. But let's say, for example, we wanted to print something. Hi. If we didn't put return here, it would say that the output is our print function. Obviously, that's not very useful to us. All right, this is g. R10. Let's see. Oh, I guess I want to, yeah, let's put this after. It'll print hi, and it'll do x times 10. And it's very useful to specify what variable we actually want to return. We can do functions of multiple variables, of course. Unit, we'll say over here, function is equal to square root. So this is the reason why you would want to use return. We don't want to actually print out r. And then you can put return r, and then, or no. Let's do return. R is $sign R, and then we'll do unit. Let's forget to do this. And we can call RG here. We'll say 10, comma 10, comma meters per second. So a string here. R is this amount of meters per second. All right, I think we can go to dispatch. This is one of the more interesting features of Julia. I can't think of another language that actually uses dispatch, but the point of dispatch is we looked earlier at addition and we saw that it had 200 plus methods. What it means to say is that for every different data type, it performs a sort of different operation. So we can define something like, the most relevant example I can think of is absolute value. So an absolute value for a complex number and a real number is very different. We define the function based on an input. So this is going to be one of our methods. If x is above or equal to 0, return x. We'll go over like if statements later. Else return negative x. Then we'll end this, and then we'll end this. And then we can print ln of 2 dot, and just to check out, we can say negative 2 dot, and it's going to say, oh, the absolute value of these are the same. But now we can define a function based on a different input. I'll show you another way of defining functions. You can do it in a single line if you just say abso x. We'll say this is a complex input. I'll say this is the square root of the real x plus match x squared. So now abso has two methods, and we can call this second method here abso of 3 plus 4 imaginary. So it's now defined for complex numbers. Here it's going to say, 3 squared plus 4 squared, square root of that is going to be 5. But our previous method still remains, where we can do this based on a float, and it's still going to give us 2. We can see what happens if we try to print this for an integer. We haven't defined it for an integer, so it's going to say no method matching. So we can also define what it returns. So we'll take this function here. We'll just copy and paste it here. And we'll say the output is a float, just so happens to be. And we can do abso again and do it for a complex number. Perfect. Any operator is also a function. We kind of saw that earlier. You know, f is equal to plus, and then f of 2 comma 3 adds it up. Wow. So we have a further discussion later. I don't know if we'll get to it. And one last thing you can do with functions, or not the last thing, but you can also define a function, and then you can say dot dot dot, and it'll take an arbitrary number of inputs after that dot. So ax, and we can say p1, comma 2, comma 3, comma 4. What did I do here wrong? Oh, oops, I'm not looking too well. And what it'll do is it'll assign this vector. The first element is going to be whatever you put as your A, and the second one is going to be this tuple as your second element. Let's see. Yeah, so there are also optional arguments that can be defined by default. This is going to be very familiar to most people. So for an object falling, we can say we know the acceleration and we know there's no initial velocity. So we'll say v0 plus a times t. You do the velocity of time is equal to 1, and that's going to be 9.8. We'll skip a little bit of this and go straight to control flow. So this kind of includes loops, compound expressions, logical operators, if else, exceptions and tasks. Yeah, I guess that's the best way to define it. There's I mean, you always try to find a category for these. They're kind of related. They're all comparison tasks, I guess, in a way, but that's the only definition I can think of off the top of my head. For loops, pretty important. So a for loop, as you'd think, and a lot of you have gone over this, but I'll go over it again. It's iterated over a known number of iterations. So here we'll do for I in 1 to 5. So we'll do this for every I in the interval 1, 2, 3, 4, 5. This is inclusive, unlike Python. So if that confuses you, that's why. For each element here, we're going to print that the element that we're doing the iteration over. And it'll print 1 through 5. We can do this same thing. And for this range here, we can add a step. So this is in steps of 2. And it's going to print 1, a step of 2 plus 1, and a step of 2 plus 3. Pretty simple. We can also iterate over any array you can think of. So help, I don't know, and so this will iterate over a list array. Do this. Iteration space. Oh, my bad. I'm tunnel visualing a little bit. Thank you, though. We'll go to. We'll go over while loops. There's like a single cell on this. A while loop is simply we're iterating until a condition is not met. So while count is less than 10, we're going to print the count, and then we're going to add 1 to the count. Goodness. And so the first element that's not less than 10 is going to be 10, and so it's going to stop right there. Compound expressions, I find these super useful. I pretty much always use them when I'm doing functions. Essentially, it's a shorthand for doing everything in a block. So we'll say value is equal to begin, and then value won't be defined until the last line. So x is equal to 2, y is equal to x squared, and then z is equal to x, y, and it's going to return z. we also terminate this with an N. Perfect. We can also just check, we can print val, and then we can, copy and paste this and print exponential for, just in case you didn't believe me. Perfect. And the colon operator is pretty similar to begin. We can say val is equal to, you terminate this with a circle bracket, colon, y, x is equal to x squared, and z is equal to x, y. This is functionally the exact same thing as we did before. And it's going to give us the same result. Next is if-else comparisons. These are pretty self-explanatory. It'll iterate over each if and see if the condition is met. And if the condition is met, it'll execute the code under the condition or under the if statement. So if x is equal to y and y is equal to z, we'll say print that this is an equilateral triangle. We can do else if only x is equal to y or y is equal to z. My goodness. X is equal to y is equal to z, z is equal to x. So if any of these are true, if any of the sides equal each other, but if not all of the sides equal each other, it's going to print isosceles. I don't know how to spell this. I'll just go with that. Else, so if the other two conditions are met, it's going to print that this is a scaling triangle. And then we end each if-else loop with end, and then we end the function with end, and we can do try of all the same sides. We'll do, since this already prints this, we don't actually have to worry about putting a print statement. We'll do this with two sides equaling each other, and we'll do this with all sides different, and it's going to print this is an equilateral, this is an isosceles, and this is a scaling triangle. Last here for the if-else is we have this question mark operator. I don't know if you guys have seen this operator anywhere else. I think Julie is the only place I recognize this from. But it's essentially you put a condition X and then you put the question mark, and the Y is going to be what happens if it evaluates to true, and the Z is going to be what happens if it evaluates to false. So we'll say X is equal to 1, Y is equal to 2. And then we'll say X is equal to Y. This is not true. If this is true, though, we'll print smart. Otherwise, we'll print die. And clearly we're dead. But if we do this again, now these two equal each other, I'm going to say we're smart. And you can see how this can get like really efficient when you're writing your code. It can make it very, very compact. So we'll do the previous function that we did before, but in a single line. So X is equal to Y and Y is equal to Z. And then we'll do, if this is true, let's print equilateral. But if this is false, we're going to check this again. We'll say X is equal to Y. So we're doing another condition, or Y is equal to Z, or Z is equal to X. And the question mark, if this is true, print ln. Just put ISO. This might not fit on your screen. But if this is false, we'll print scaling. And so I think this is the last one, yeah. Oh, we forgot our end. And we'll copy and paste these. It's just, we're just doing the same evaluations to see that it's the same thing. And it turns out, yeah, this is the exact same comparisons that we did before. Yeah, we'll go straight to this. We'll approximate pi using our for loops and our if-else statements. So no need to copy this around, this down at all. This is just like a little demo. Sum is equal to 0. I'm going to solve for pi using this equation that we have here. It's an infinite series. We'll do it to n terms. And then using this identity that 4 arctan of 1 is equal to pi. We did this in our first meeting, so it might be a little familiar. So we'll define the sum that we're going to keep adding to, and we'll define this n, which is going to be our count. So while n is less than or equal to n, sum is equal to itself plus the term above, so -1 to the n divided by 2 times n plus 1. So this is just our series here. And then we're going to add 1 to our count. Then we're going to end this. Then we're at the end of it, we're just going to print pi is equal to 4, or do the interpolation 4 times sum. Then we'll end this here. We have our function. We'll do our approximation to 1 million terms. I think that's right. Yeah, 1 million terms. Turns out it does it pretty fast. So here we have pi to maybe 5, 6 digits. One thing I wanted to show is that, let's do this for, let's define an n here. N is equal to this. If you use add time, you can determine the amount of time it takes to run a function. So here we're going to run prox, and it does it. See, yeah, it does it in about 0.095 seconds. One thing that I wanted to show is runtime disconnected. What the heck? Oh, here we have the exact same function, but in Python, and I wanted to just check the time here. And it turns out this is 0.5 seconds, which is pretty much an order of magnitude larger than what we can get in Julia, and this is without any optimization. So just a little bit of a proof that this is a very well optimized language. What's up?
Is there anything about this approximation for pi that leads to the thing where we're off by a digit at one point and then there are some more right digits after that, if I'm remembering my digits of pi correctly?
Yeah, I believe it stops at here.
Yeah, I think you change that 3 to a 2, then I think it's.
Yeah.
It's 5, 3, 5.
We got another digit. Yeah, so this is just a Taylor series. We're doing it to n terms, and you know a Taylor series gets better as you add more terms. It's that simple. And here we did 10 times the amount of terms, and we got one more significant digit. Yeah, it's a lot. It is not a very efficient way to do pi, but it's very simple to implement. I have another example here, but we're running a little low on time, so I recommend looking at it in the full document. We list all the numbers between 1 and n that are prime. It's kind of big, so we won't really go over it too in depth. So exceptions. I want to go over this fully, but I'll just say you can do an error or the throw statement. Essentially, you can create an error by using the throw statement, and if you use the error method, it's doing the exact same thing. But here you can specify, oh, this is a domain error. Error, to. You can see how this can be useful. Is so this will throw up an error, domain error with 2. Operation on 2 is down. We can kind of do the same thing, but this time we can just use error. Error is a more general term for it. So we'll do error, wrong. Pretty simple. You can replace or you can put the catch statement to check if something is a value to an error inside the try statement, and if so, it runs a different part of the code. We'll skip a little bit over this section too. This is some of the less important stuff, I would say. But we'll go to constructors, and for people that are used to object-oriented programming, this is the closest thing you have to it. In general, us being math majors, being physics majors, some of UCS, yeah, it won't be that useful to know about objects to begin with. But we'll define a struct. This is pretty much an object. This struct has two characteristics, real and imaginary. We'll make an object with this, and we'll say it's complex junior. So this is like complex number. And we can consult the real value of complex junior. And it'll tell us complex junior has a real value of 1, as put here. So they can be redefined based on the input. So one cool thing is you can say complex junior. If you're not given an imaginary argument, is going to be equal to complex junior. But x and the imaginary is 0. So we can do this again. We can say c is equal to complex junior of 5. And we can see that c dot imag is going to be equal to 0. We can do the same thing here. This is just a little bit funny. You can say if we're only given one input, then both the inputs are the same. And we can, yeah, complex junior. And we can say c is equal to complex junior 5 over here. And get the imaginary number, and it's going to be 5 as well because of how we redefined it. So we'll do a different struct vector, just to kind of show you can define each of the object parameters according to a data type. So we can say this is an integer number, and we can say imag is also an integer number. We can end this, and we can say b is equal to vector 1, 2, and as you'd expect, the real value is going to be equal to 1, but now we've restricted what kind of goes into our object here. So this is a bit more complicated. If you make a struct and you say it's complex n, we can define real and imaginary numbers, and then we can kind of put a condition besides a data type that has to go into our complex. So we'll say real imag. So if real is equal to 0, or imag is equal to 0, do the operator here. We'll say that number is pure, complex, or real. So in this case, we're going to have a number that's complex, but one of its values is going to be 0. So you can better say it's only a real number or only an imaginary number. This checks off. Otherwise, we say new of real, imaginary. So it let us state that, oh, it's passed the condition, so now we can make the object. So complex n 0, 2. And as you'd guessed, the number is pure or pure imaginary. The number is pure imaginary or real. So it's kind of silly to represent it as a complex number, is sort of the intended message. But if we have both of them, it's going to meet the condition. And it's going to say, oh, the real value is equal to 1. So we're done with constructs finally. We're going to talk about working with arrays. Pretty important. Let's say we make an array with random elements. So 9, 9. It's just going to make an array with random elements for each element, and it's going to be a size 9 by 9. We can. Yes. Yes, you can. I mean, if you wanted to, this is not the best way to randomize stuff, but if you wanted to do it uniform over 10, that represents your boundaries. I think that you add some bias though if you do that, I believe, but I could be wrong. Anyways, we're going to index this over the first element of our A, and we're going to get a value back. Now, we've only indexed one element, but regardless, we've gotten the first row, first column. In general, if you go to Python and you do something like A1, 1, that's what's going to give you the first element of your first row and your first column. But here it kind of just assumes that it's the first column when you choose your first row. So that's very, very important to keep in mind. If we want to take like a row, for example, we'll say define the third row, and we'll say take all elements of that column. and it's going to print out the row. It's going to do this sort of vertically. Or no, I don't think that's vertical. No. Yeah, if it was vertical, no, that is vertical. My bad. It's a 9 times 1, so it's a vertical vector. This is kind of a spoiler, but if you do this, which is the transpose, it's going to do an actual row vector, which is a 1 by 9. Forget you saw that. We can take the column. Similarly, this colon represents taking every index over that row, and we'll do it over first column. And it's going to be a column, and it's still going to be defined as a vertical vector. So this colon operator works in a few different ways. We'll define n is equal to 4. And what this represents here is we're taking the number 1, 2, 3 until n, which is 4. And then we'll do this for every element, for every column. So now we have a 4 by 9 array. This is the first dimension, essentially, 1 through 4. And this is the second dimension, which is all of the elements. And we can do this. And if you use a single colon here, it's actually going to flatten the array into a single vector. By default, we'll get this out of here. But the last thing, and a little more important, is that we can index a specific array. So let's say we want the first, the fifth, and the third elements. And we say A, first row, indices. So this is going to be a 3-element vector, but it's going to be the first, the fifth, and the third column position from row 1. And you can also say end. This is like a -1 in Python. It takes the last element. And if you wanted to take the second to last element, you do n -1. So expect it.
Number in A, like an index, like A1, then it prints only the elements in the first column, right?
Yes.
Say A2, then it will be the first column, second row, that particular element.
Yes, yes.
So what is it?
I could not tell you. I thought of a use for that. I guess like in the case that you want one exact element or you want one exact row, it saves you one character that you have to type. I can't think of a use for it, but that's just how it is.
Like,
oh, really?
yeah.
I didn't experiment with this. So if you do this. Yes.
So what about the other column?
Oh, I mean, you could just you could define like both inputs.
If you increase the index, we'll just loop.
No, what I want to know, like, why do they have it specifically for the first column when you have a lot of columns in a matrix?
I wish I knew. It's like such a dumb thing.
A25, just one argument.
Well, 25 doesn't fit. What do you want to do, like A3, for example?
No.
And I still give you some random thing. I just
It will give you something.
That's what you think.
Yeah.
Yeah, I guess it loops back around, yeah.
Yeah. Is that in the middle? Or is that in the same version?
It's in the first.
Yeah.
column, 25th row.
It just loops the one column. It doesn't go.
Yeah. Yeah, that's a good question.
It's probably some weird hard coding. That's all I got to say about it.
Yeah. I mean, let's see. This is going to be still in this first column, I believe. 25 is going to be you looped around it twice, and then it's going to be I think this element. So.
Wait, try like 11 just so.
No. Oh no. This actually does go by column. I did not know that.
I think it's-
Yeah. My guess is if you flatten this into an array, so if you did it as like a as we've demonstrated here, where this makes it an 81 element vector, the 25 is going to be the 25th element in this. So maybe that's a little bit intuitive in a way. I can't possibly think of someone doing that. I don't know. It's just so silly. I guess, but I don't know. I would just do both indexes, you know? Or I guess it's one for loop. So it's going to be the same amount of iterations, but you're going to have to write less. That's
less hard to deal with.
yeah. I mean, it's the syntax is going to be prettier. It's going to be more compact, if that's what you mean. Yeah, that's true. Yeah, nobody's going to look at your Julia code, man. I'll be honest with you. True, true. Maybe I'm underestimating people. We can actually make different types of arrays. So if you don't add commas here, this is going to be a row vector. So we'll take the size of this by using the size function. And it's going to tell us this is the first dimension is 1, and the second dimension is 3. So that's a row vector. We'll copy and paste this, and then we'll add commas between each element. Now we've made a column vector, so the dimensions is 3 by 1, where the second dimension is not really represented. Don't use commas when dealing with a 2D array. I learned that the hard way. The transpose is maybe as simple as you'd think. We can define b is equal to, we'll make this an array. 1, 2, 3. And then we'll say print the size of b. So 2 rows, 3 columns. And then we'll do this. We'll go ahead and say transpose b. And then we'll print the same thing here. So our first array has dimensions 2 by 3. We did the transpose, so now it's 3 by 2. You may also check that we can just redefine as b apostrophe. Since this is all real numbers, the apostrophe operator is the exact same thing. It's definitely more short, so that's why you would use it in general. Or if you actually had a matrix of complex numbers. Here we have 2 vectors. My next trick is to fuse them together horizontally. So we fuse them together horizontally. So this is a 1 by 2 and a 1 by 2. So we're just listing them out like a little snake. We'll copy this code. If you put bcat instead of hcat, it's going to concatenate them vertically. So now it's a 2 by 2 matrix. We added them one on top of the other. We don't need this. Important functions and methods. So this is just a bunch of stuff that you might use in linear algebra, for example. So this is an array of ones. Pretty similarly, we can do an array of zeros. This turns out to be surprisingly more useful than you'd think. We can do, I think we already defined A. We'll do sum of A. And this is going to sum over the elements of A, which is 1, 2, 1 plus 2. We can do the maximum of A, which is going to return the highest element of A. We can do the minimum of A, which is going to return the 1. Similar, creates a matrix with the same dimensions. So we have our A is a 2 by 2. So we'll say B is just a matrix that's similar to A. And it's supposed to do 0 here. I can't for the life of me figure out where it does this. Yeah, but this is like way more digits, you know? No, the float 64 is e-16. This is float. It's like one. What is this? Like maybe 5? No.
It's like a big float.
Yeah, it's probably a big float, but it says float 64 here. That it's confusing. This is supposed to be 0. Is sort of the point. It instantiates it as pretty much 0. We'll also skip this. We have a bunch of comparisons here to Python functions and MATLAB functions if you want to look at that. This is very, very useful. At first, I had to look up how to do everything from Python to Julia, and now I'm glad I did. It makes a big difference. Packages are next. If you want to add a package and use it, you say using package, which is a package in and of itself. That's a little funny. And then we'll say package add the name of your package. And to use it, we'll say using package. And it's not quite like an object where you have to put a funny packages dot and whatever like a part of the object you want to use. It kind of does like, I don't know if anybody's seen this from SymPy or from NumPy import this. So now you don't have to type numpy dot whatever function you're using, numpy dot cosine. It's analogous to that. We'll do some calculus. So we'll define a function of x, and it takes in a vector, x1 times sine of x2. So a vector with 2 elements. This will be fine. And we'll use the for_diff package. You can maybe guess what this does. It takes derivatives. We'll say this df is going to be equal to x maps to for_diff dot gradient. Our function fun and do derivative for x. So x is a 2-element vector, so it's going to have a derivative with regards to the first element and the second element. And this is going to return a list with the first derivative of the first element and the derivative of the second element. So we'll run this. This did this surprisingly quickly. Usually pre-compiling packages takes a long while. But thankfully not. Here we'll get a column vector. This is going to be 1, and then we're going to do pi tab over 2. So I just set it here, and you might just want to believe me, but this derivative with regards to x1 is equal to 1 and x2 is equal to pi over 2 is going to be equal to 1. So we'll get a vector, or diff not defined. No, don't actually. So you only have to do this if you want to add the package. And this ran. Oh, haha, funny. It was 1 capital letter. We love that. Anyways, this is the derivative with regards to x1, and this is the derivative with regards to x2. So we wanted the one with regards to x1, so we'll just consult the first element of that, and it is, as we surmised here, 1. We'll copy and paste this, and we'll do the second derivative, but then we'll get the second element, so the derivative with regards to x2. It turns out that if we plug in what's above, we will also get 1 as defined here. Integrals, solving integrals, you can make all of your own functions, but you never should, because people have done it better, and that's the unfortunate truth of the situation. So we'll say this is integral. Maybe this isn't the best name, but whatever. Integral is equal to exp negative x squared. This is a pretty classic integral. Maybe you'll recognize it. And then we'll say integral and error. The function we're going to use returns the integral and then the assumed error of your method. So quad gk, and this is actually all not capitalized, of our function over the integral 0 to 1. And then the relative tolerance is just, I think, the minimum or the maximum allowed error. It's not even the step size. It's a bit more confusing. And it'll do the integral, I think. Yeah, it did the integral. We did it. Now, what we want to do is we'll define a couple of functions, and we'll use probably one of the most important packages, which is plots, so we can plot stuff. So x times exponential of x. We'll define a function that e.g. takes the derivative here above, and we're going to return, I'll just copy and paste this. It's a lot of words. We're going to return this of our base, which is our g here, our x times e to the x. And then we'll end that. So it'll return the derivative for a specific x. We'll make something similar here. So this will be our integral of g to the x, And then this is going to be our quad GK function, our base, from 0 to x, and then the relative tolerance. And we'll just set it to something reasonable. And then because we don't want the error to be included, we'll return the first element of this vector. This is a comma. This is classic. Here we go. Perfect. So we can check these and plug these in. One thing I want to check is if they equal the actual integral done exactly. So these are the actual integrals and what they resolve to analytically, so not numerically. So we're going to check our derivative, check dx, and then we're going to check our integral, check into x. We're going to see if these equal to each other, and the only way to do that, really, at least visually, is to plot them. So we're going to use the plots package, using plots. This usually takes a year to load. I could not tell you why. And meanwhile, we'll write these down. X is equal to 0 with a step size of 0, 0, 1 from 0 to 5. Then we're going to plot x comma dg dot x. So we add this because we're doing this for every element in an array. We're doing this operation. And this will plot. Expects that x is an array, perhaps meant. Oh, oops. Okay, it turns out we're doing this with regards to one element, so we should use the derivative function. That's my bad. We're going to plot this, and it's going to give us the plot if it ever finishes. Here we go. Here's a plot of the derivative of x with regards to, or derivative of g with regards to x. We can add another plot by saying plot, capital, and then we might as well plot our integral. And it's going to plot them on the same figure. We're going to copy this, and instead we're going to do our exact functions. So what are those called again? Check D. Check D. This checks our derivative, and check int. This checks our integral. And it turns out they're pretty much the same. So we've done the integral and the derivative correctly. Linear algebra. Let's see. Okay. Define a matrix. This is a matrix. Why do you do this to me? Space before. This is a matrix. Perfect. We can take the inverse of the matrix with inverse of A, but we can also do the actual inverse operation by doing it to the power of -1. And to unlock a few more of these linear algebra operations, we're going to import this package using linear algebra, case sensitive. We can get the determinant of A, which is just going to be 2 times 4. We can get the, or let's work with some vectors. We can do this is equal to A, and this is equal to B, 5, 7. We can do the dot product of A, B. This will give us the dot product of A, B. Furthermore, we can take the norm of A. So this is going to be 1 squared plus 2 squared square root. It's going to be 2.23. One useful thing, and you might use this a lot, is you can make a diagonal matrix out of a vector. So we'll make a diagonal matrix out of this A. And it'll give us a matrix with the diagonal being the elements of A. Let's see. Very important, we can take the eigenvalues and the eigenvectors by doing eigen A. It'll tell you the values, it'll tell you the vectors. As expected, it's 2, 4, since we have a matrix over here. It's 2, 4. Pretty simple. We can solve linear systems very, very quickly with matrices, and the syntax is very, very short. say we have this matrix, half and 8. Our matrix A is 1, 2. So if we do A divided by B, we're solving the system. AX is equal to B. So X is equal to 1/2, or is that how I define B? Yeah. Or no, A is over here. Yeah, I'll get this again. We're solving 2x is equal to 1/2, and then 4y is equal to 8. You'll find that the solution is correct. X is equal to 1/4 and B is equal to 2. Very simple way to solve linear systems. And we'll get to the extra section. There's a lot of stuff here, but I think most of it is really, really interesting. This is how to optimize your Julia code. There's a lot of ways to do this because Julia has a very specific compiler. So one thing to know is that Julia is a row major programming language. Any other programming language that you can think of is probably column major, which means that if you iterate along rows, it'll go slightly faster in your for loops. No need to write this down, it's a lot. So we'll do n is equal to 100, u is equal to rand, n, comma, n, and then we'll copy and paste this twice. Say r. So we're creating 3 1,000 by 1,000 matrices, and we're going to write a function, row, u, comma, v, comma, r, and we're going to do 2 for loops for I in 1 to n, for j in 1 to n, do rij is equal to uij. Bij, and you'll notice this is pretty much just adding the 2 of them element-wise, so it's nothing we haven't dealt with so far. We'll finish this off. Redefinition of constant r. No, it's outside of the function. I'm not sure. Let's just say this is what's a variable y? No, y is defined. Q. Okay, so this works. Now this is inside the function, so defining q here doesn't affect the q inside of the function. But we're going to check how much time it takes to do this function for u, comma, v, comma, q. It takes about 0.7 seconds. We're going to take this same function here, but instead we're going to do it by, did I check this twice? Yeah. We're going to do it by column. Yeah, we're going to do it by column. And I'll just copy and paste this here. We'll name this column. So if we do column, let me take the time. Column u, comma, v, comma, r, q. This will take way less. That's because we're iterating along what is really a cache line. Cache, C-A-C-H-E. Yeah, I couldn't tell you. And when we iterate along a cache line, and I might have confused the row and column here, but I think you get the point. When you integrate it, or when you iterate along a cache line, it takes substantially less. The allocations are the same, but it goes way quicker. We can divide types of allocation into stack and heap. So we're actually going to use some of these functions again. They're pretty useful for us. So this function is just going to be our stack function. A stack allocation means that we save things in contiguous memory. So by the time you run it, you don't have to actually allocate anything. So this is how it's kind of done by default and how we did it earlier. V, I, comma, j. We're assigning, or we're allocating something to S here, but it's being allocated in stack, which is a good thing. And we'll just do something random for Q. Q is, you know, It doesn't really matter. It's equal to S1. And we can check the time, do the stack. U, V, Q. It'll take 0.8 seconds. But if we do this with heap, what we're doing is we're going to add a parentheses or close brackets here. What this does is we've made S a variable for which we cannot determine the size very conclusively. And the problem with that is that now we have to allocate it, and it's not known by the time it's compiled, so it has to be determined when compiled at runtime. So we'll call this heap, and we'll see the difference. It should be pretty long. It's an at least 2 times difference. The allocations are 2 times as much. And so it's a very simple way to make code like some n number faster. This is pretty obvious, but if you increase the amount of allocations, it makes for a longer time. Let's see. We'll skip over this too. It's all very intuitive, I think. We'll go onto the final section, which is the compiler and the type inference algorithm. A variable type tells the compiler how to store it, and when you go to runtime, it decodes it as some allotted memory. So this is why C is very, very quick. In C, you say, before you define anything, you say what type it is. So if it's an integer or a float, and your output is also going to be defined as a specific type, whatever you want it to be. And the good thing about that is that everything is static, and so everything is saved in stack. So operations are very quick. The polar opposite is Python, where we allow untyped variables to be untyped prior to running them. And there's no real way to actually type variables prior to running them in Python, which is why there's like an order or 2 of magnitude for pretty much every single operation that you can make in C. The way Julia does it is a little strange, but it works pretty well. This here. The way Julia does it is you don't define the types beforehand. You've seen that we don't define every single type, but Julia runs a type inference algorithm, and it goes through every single part of your block, and it says, this is an integer, this is a float. We're going to consult your method that takes in an integer and a float. And essentially, after that type algorithm, it runs exactly like C. So the only thing that increases the time it takes for Julia code to run is that type inference algorithm. So when it's negligible, it runs exactly like C. We'll see some examples here. So A is equal to random 10, 10. B is equal to 8 dot. Here I'm trying to paint an analogy. What we're doing with Python is essentially we're at runtime, it's kind of like if we were calculating each specific element instead of consulting it from a list. So if you, what's quicker, like calculating an element in a list or taking an element that's already defined from that list? And this isn't exactly how it works. This is funny. This isn't exactly how it works, but we'll do time of B. How much does it take for us to consult B? It's very, very small, and exactly 1 allocation. Now, how much time does it take for us to perform this operation on A, which we've already performed over the whole array? Well, clearly, a lot more time, but a lot more allocations is probably the worst thing. So you might think that this means that making a function of a specific type will be faster when you get your method, but Julia is smart enough to consider when you make an untyped function, and it's more like it makes it as a generic function over every possible method. So when you don't define your variables in a function, it's pretty much bait every single possible variable type as its inputs. So you don't save a lot of time by making a function with a specific type. I think the last thing we'll go over, we'll skip this for a little bit, is we're going to use interactive utils. And this is going to give us a glimpse of how Julia goes over its type inference algorithm. We'll do a begin block, A is equal to 2, B is equal to a complex number, We'll make this very varied so that Julia kind of has a hard time doing it. B plus Y. Return C plus D. I'm just defining a random function. It makes this integer. It makes this complex number. It multiplies them and allocates it to C. And then it, is this right? Yes, and then it defines a D of through B plus Y. Where's the Y? Yeah, okay. No, this works. And then it returns, and this is the last operation, C plus D. So we'll check out the time, and then we'll use the code warn type function from the package we just imported. And we'll set two random inputs here, so a float and an integer. Or run this first. And this will take a while. But this is how Julia sees the function that we're going through. It sees a self, which is the function itself. It sees x as a float. It sees y is a integer. We define C here, yeah, we define D as a complex because we're summing a complex plus whatever y is, which is an integer, and the output of that is a complex. It sees C, which is a, an integer, times a float, which is a float, et cetera, et cetera. And then the body itself is the return statement, and it's going to return a complex number. So that's how Julia sees the function inside that you might not be able to take a look at. I think it's very interesting, and it can tell you why your function is not working. But that's that. That's it for everything. We went over everything as quickly as I could. We skipped over a lot of stuff, so maybe look at this thing again if you'd like to. But yeah, that should do it. We're done. Thank you for coming. What's up? Anything wrong? No. Oh, yeah, good. Yeah. Oh, sorry. 2 hours is a long time. Oh, true. True. Oh my God, I spoke a lot. Stop recording.